Classification of elements into S, P, D and F blocks. So we will study here characteristics, groups and periods, how we determine the elements and during groups and periods. So first we'll see electronic configuration in a period. What does this means here? Electrons are configured in the electronic configuration in order to increasing order in terms of period. So let us see one example. Hydrogen is 1s1, helium is 1s2. Like this, lithium S will be your 1s2, then 2s1. So it is increasing order. So 1s2, 2s2. Then after this, beryllium will be 2s2. Beryllium will be your 1s2, 2s2. So like this, configuration is filled along the period. So here the last orbit is one determines, if 1s1 is there, the one determines the period of the particular element, and one this electron present on the orbital determines the group number. So we will see in this is differ from block to block. So like the sodium is also there, 1s2, 2s2, 2p6. So 1s2, so this is K cell, 2 means L cell. L cell contains 6 plus 2 electron and 3s1. This is your third period. This will denote the third period energy cell, and S1 electron determines the group number. So this belongs to group number 1. Now for configuration group, just I discussed. So if the all configuration, the last orbit of the last cell of the electronic configuration determines the group. So they have same number of electrons present in them. So for alkali metals, whatever group is there, it will be always NS1, 4s1, 5s1, 6s1, whatever period is there, this will determines the group number. For alkaline earth metal, this is S2, NS2, 2s2, 4s2, 3s2, 4s2, 5s2. Like boron family, so this will be your 3s2, 3p1, then 4s2, 4p1, 5s2, 5p1. Like this series is going on. So P and P1 determines the group number 13. So on the basis of electronic configuration, the elements are grouped into 4 blocks. So these blocks is S, P, D and F blocks. So it is given on the name of orbitals, and electron, the last electron enters in the S block. That's why it is called as S length. If the electron into P block, it is called as P block. If the electron into D block, this is called as D block. Likewise, it is called as F block. So let us see some of the properties. So S block elements, differentiating electrons. This means the last electrons enters into the outermost subcells like NS1, NS2. So this is called as alkali earth metals. If the last electrons into the NS2, so this electron is filled. This orbital is subcell is filled. So this is actually alkaline earth metals. Colors I have also mentioned. The color of sodium is golden yellow color if you burn it. If you burn potassium, it will give you violet color to the flame. Now see for P block elements. In P block elements, it belongs to group 13 to group 18, and the electronic configuration of element present in this group 13 to 18 is NS2, NP, 1 to 6. So 1 to 6 is empty. This is full. This is your NS2, and this is full. It is full, and this N, but this is empty. But both have same principal quantum number. And is both have same. So NP1, NP2, 3P1, 3P2, like this goes on. So 3P1, 3P2, for example, I'm telling you, 3P3, like this it goes to 3P6. After 3P6, it will again come into next subset. So this is going series. So these elements are called as P block element that we have seen in a previous table. D block elements. In D block elements, the differentiating means, again differentiating electron means last electrons enters into the n-1 d orbital. So this is your n-n d orbital is there. So this again belong to group 3 to group 12, means there are total 10 groups are there, and these are transition elements, and the configuration is like this: n-1 s2 p6. So it will be your n-1 s2, n-1 p6, n-1 d. So electrons will be filled here 1 to 10. Accordingly, NS1 or 2. So here 2 electrons are there somewhere. In some element NS1 is taking, some element NS2 is taking. So scandium, you can see example, argon 4s2 3d1, chromium 4s1 3d5. So 2 electrons are there. 2 subsets are there, 4s1 3d5. This is for stability purpose. Manganese 4s2 then 3d5. So 5 is going on. 5 means again this group will be 7. 5 plus 2 7. So again for copper, again 10 plus 1 11, so this belongs to 11. So this is your n minus 1, this group is n minus 1, you can see n minus 1d. So first is n, this is the outermost orbit, this is less than this, so this electron is going to fill the d orbitals like this 3d. So I have given for 3d series scandium to zinc, for 4d series yttrium to cadmium, 5d series hafnium to mercury, and 6d series actinium. So this is incomplete series, so it is not given completely. So after this we'll see next is your f block element. So it again differentiating electrons into the n mass 2 f orbitals. So again they have 3 incomplete outermost cells, that's why they are called as inner transition or f block. 3 incomplete outermost cells means like 4s 4p f, these are incomplete. So we will see here. Let us take some series of the f block elements. So some series of f block elements are 4f and 5f I have taken. So in lengthenize this f block series, this first series or 4f cell is called as lengthenized series. It belongs to lanthanide to lutetium. So atomic number of lanthanide is 57 and atomic lutetium is 71. So this is your lanthanide series, which goes from 50 to 71. So for this first series you can see here, if you put this value here, f block is empty, so this f is filling. For lanthanide it is 0, for cerium it is 1, for lutetium is your 14, and remaining 5s2 5p6 5d1 6d is complete series. But you can see here 6p is 0, 6d 5d is incomplete, so 4 is, so again 3 series will be always incomplete. So here 6p 5d 4, it will be incomplete. Similarly you can see actinide series. So here differentiating electrons into the 5f electron. Differentiated electrons, again I said this electron is the last electron into the orbital, going the orbital. So here again this is goes from actinide to lawrencium, F189 atomic number to 103. So again this series is 50 F1, again you can see 5F1, so 76D 7 to the other incomplete series. So this is going to fill, this will be constant in except some of the cases this will constant, otherwise it is constant. So here only main f orbitals being filled up to 14. So this is, they also consist of 14 elements, and lanthanide also consists of 14 elements. So lanthanides are called as rare earth metals. Actinide is called as transuranic elements, means these elements which are prepared mostly after uranium, so they are called transuranic, means artificial prepared elements. Now determination of group and period if atomic number is given. So this I just discussed how to find the how to locate a period. So period is located by the number of outermost cells. So I have seen outermost cell is supposed 2s1. So this is outermost cell. So 2s1 means 2 is the period, and differentiating electron is 1. This is your second period. Second period means electron is present in the second period of element, and 1 means group. So look at the group and block. So S block, suppose is the number of S electrons present in the valence cost block. For P block, group number is nothing but the number of S electron plus P electrons plus 10. So you have to add 10 also. 10 plus P electron in valence cell, but this will give you P block. Example I will give you after this. For D block, group number is called as number of n minus 1d. So you have to take this electron, this is called as penultimate cell. Penultimate cell means one cell which is lesser than the outermost cell. So suppose outermost cell is 4, so we have to take 3. So this is called as penultimate cell. This principal number is called penultimate cell. So what outermost, you count the outermost electron plus penultimate electron. So this will give you group number. For F blocks, I discussed the element with atomic number 58 to 71 are placed in atom number 7 in 6th period and group 3 third in group 3. So both these blocks are present in group 3, but one will be your 6th period. Elements with atomic number 90 to 103 are placed in atomic number 89 in 7th. So for F block 1 group 3 6th period, for 7th period group 3 7th period. So for 7th period atomic number will be 90 to 103, and for 6th period atomic number will be 57 to 17. For this you go through the periodic table, you will understand automatically. So again, so we see, let us see example. Suppose we have atomic number 8. So write the configuration 1s2, 2s2, 2p1. So how to find group and period? So I said for group take the last outermost electron. So outermost shell is the here 2p is the outermost shell. So 2 will give you period, and 4 will give you your period. So for period again we have to take total number of electrons present in outermost shell. So 2 electron from the S and 4 electron from the P, and you have to add 10, so it becomes 16. So this element is belong to group 16 and period is 2. For this one, see here, so this is some argon 4s1, so we have to take last electron. So 4 will represent the period, 4 will represent the period, and S1 means again S block, we have to take 1, so 1 belongs to group 1. Suppose the atomic number of element is 17. So in 17, suppose you take neon. So neon we can write here 4s2 3d3. So this is 4s, is the outermost electron. You have outermost orbit is CC, will denote the period. So this is principal quantum number, and this will give you fourth period. But electron will not count, but this will not give you group. Group will give you lesser than this, because they have D subshell also. So formula for D block is n-1d plus ns electron. So n-1d means 3. Okay, so here you write here 3 electron. We have to take electron for group. Now we have to electron and add 2 here. So 3 plus 2, 5. So this belongs to group 5. Besides, we have some terminology left. So we have to understand, because they are used to ask in the examination, like what is typical element and representative element. So these are actually elements of second and third period, because they represent the properties of the respective group. So they are called as representative elements. So second, third means like beryllium, aluminum, carbon, silicon, like oxygen, sulfur. So these are the representative elements. What is diagonal relationship? So it is a phenomenon in which the first element of the group resembles the closely with second element of the next successive group. So we can see a second and third period. This often happens with the second and third period. So these are the first element of the group second period, and these are the second third period of the elements: sodium, magnesium, aluminum, silicon. So it is says that the first element of the group resembles the second element of successive group. So these are the successive groups and second members successive group, and these are the first members. So they have similar relationship. So their property is also similar. Beryllium also matches with the aluminum, and boron also matches with the silicon. So actually they have similar properties, and there are only 3 elements which shows diagonal relationships. Besides, one more element is called as bridge element. So bridge element, just like a bridge which is connecting something, two things. We connect something, two things, 2 elements. So these are the typical elements of third period. So this is typical third period, and which is acting as a bridge between bridge elements. So they have 2 mixed properties, 2 subgroups. So we have only one example. So this is your second period, third period. Third period, magnesium. Magnesium has a property of group 2 elements, and magnesium has a property of group 12 elements. Group 12 element means 2b is also called. This is called 2a. So that's why magnesium is called a bridge element. It has property of calcium, strontium, barium, radium, or zinc, cadmium, or mercury. That's why magnesium is called as bridge element. Now after this, we will see how to give the nomenclature of element having atomic number greater than 100. So if the atomic number is greater than 100, so UPAC has given some special criteria to write the nomenclature of these elements, like 101, 102, 103, 104. So how to understand and how to write it? So first let us see their numbers of all the elements in letters given by UPAC. So number is 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. So for 0 it is nil, name is nil, NIL nil, and abbreviation is N. Similarly 1 UN for abbreviation U, 2 is called as bi B. Similarly 3 tri T, 4 is quad Q, 5 is pent P, 6 is hex H, 7 is sept SCP sept. So this is sept means S. 8 oct O, 9 ENN in. Now how to write the names? So suppose number is 101. So according to UPAC, so 1 is your un is here, and 0 is your nil. So un dash nil. Then again 1 is there un. So 1 0 1, and you add in your side ium. So un nil unium, un nil unium. So this becomes your UPAC name, and you can write here U and U. So this is a symbol. So you will use the name of 101 element. Similarly, 1119. So 1 for an, 1 for an, 9 for en. Enium. So UUE. This is U. This is U. This is E. UUE. Capital U, small u. This is the UPAC name of the 119 element. Now if you take 145. So in 145 again, 1 is un, 4 is quad, 4, and this is 5 is 5. So unquad pent, and then you add suffix ium. So unquad pentium. So U, Q, and P. So this becomes the nomenclature of this undiscovered element 145. Similarly, you can write any names based on names given by the UPAC given by the UPAC community. So we can give the name of any unknown element is officially like this one, without giving any particular name. This creates confusion, but with the help of this type of numbers, we can understand the name of the element and we can study their properties.